Here in this video, we are talking about a process called something like a polytropic process. What is a polytropic process? Is simply a process that is describing a reversible process. That means it can come back to its original state in the other way and involves change of both heat and work. There shall be exchange of heat and work and so on, and a specific combination of properties, thermodynamic properties remain constant, remains constant. So here we will say the relation between the pressure and volume is PV power n equal to constant. This n value depends on the kind of a polytropic process. It could be a different value. So we can also say if required P1 V1 power n equal to P2 V2 power n and so on equal to constant. This kind of a process is called something like a polytropic process. So once you understand what is a polytropic process, we would like to derive an expression for work done in polytropic process. Work done in polytropic process. So it's a simple expression for the work done. We can say when the pressure is variable, because here pressure is variable, work done can be identified as integral of P dV, where volume is varying from P1 to P2. But we don't know the value of the P. We are integrating with respect to volume. Here we have a P who is not a constant. So being PV power n is constant, P can be written like constant by V power n or constant V power minus n. So in the place of pressure, I shall write this expression in terms of volume. So I can write that as in the place of P, C is a constant, volume power of minus n dV, where volume is varying from V1 to V2. Now we have a formula in integration. What is that? Integral of x power n dx equal to x power n plus 1 by n plus 1. So in the place of n, we are having a minus n. So what happens to that? Let us try. We are having that equation. That implies work done equal to C is a constant that can be written outside, V power of minus n plus 1 by minus n plus 1, where volume is varying from V1 to V2. That is, C 1 minus n can be written outside this one, V2 power of 1 minus n minus V1 power of 1 minus n can be rewritten. I can apply that C to inside as 1 by 1 minus 1 of C V2 power 1 minus n minus V1, C, taking this C inside, V1 power of 1 minus n. In the place of this C, I can write either P1 V1 power n or P2 V2 power n. As the neighboring term is V2, first I will write P2 V2 power n. That implies work done equal to 1 by 1 minus n into, in the place of C, P2 V2 power n multiplied by original term V2 power of 1 minus n. Minus in the place of this C, as the neighboring term is V1, I will write it in terms of ones, that is P1 V1 power n, and multiplying term is V1 of 1 minus n. So if you simplify this term further, 1 by 1 minus n of V2 power plus n and minus n will cancel. So P2 V2 is remaining and the other term P1 V1 is remaining. So what is the equation that we have is work done in the case of a polytropic process is 1 by 1 minus n into P2 V2 minus P1 V1. So we can also say, being an ideal gas equation for an ideal gas of 1 mole, P2 V2 PV can be written like RT. So P2 V2 can be written like RT2. So R by 1 minus N of T2 minus T1. So we can write the work done format either this way, depending on if the temperature is given in terms of if data is given in terms of temperatures, or if the data is given in terms of pressures, we can use the above relation. So we can rewrite this relation as R into delta T by 1 minus N. That is the second part that we would like to derive, that is work done. We have derived the expression for the work done, right? That part is over. Yeah. Now I would like to see what is something about specific heats of that gases, right? What is the specific heat? We know if you want to talk about specific heats, we'll start talking by saying something like, we know as for the first law of thermodynamics, dq equal to du plus dw. In the place of dq, I can write as for the definition of Cp, ncp dt. In the place of du, I can write ncv dt. We have done this discussion many times. Please look into the previous videos if you don't know from where I am writing this. I am writing this basing on the definition of Cp as amount of heat required to convert unit mole of substance to rise the temperature of unit mole of substance by 1 degree centigrade. So you can rearrange the terms and get them. And in the place of dw, like what we have derived just now, I can write this nr delta T by 1 minus N, right? So be careful. This N is different from this N. This is number of moles, whereas this is the degree by which the power is being calculated, right? So they are different. I can cancel this, of course, this number of moles everywhere. This delta T also can be cancelled everywhere. The remaining relation is Cp equal to Cv plus R by 1 minus N. That's the relation that we have between Cp and Cv. Now, we want you to solve a problem. B we have done now. We want to do a C now. So what is that C? An ideal gas is saying in such a way that PV power 3 is constant. Our general format is PV power n is constant as per our formula. That implies here n equal to 3. And he wants you to write relation between Cp and Cv, right? So we have a relation Cp equal to Cv plus R by 1 minus N, but that n equal to 3. So Cp equal to Cv plus R by 1 minus 3, that is Cv plus R by minus 2 or Cv minus R by 2. You can write the relation between them as shown, right? That's the relation between Cp and Cv. That's what we are doing everything about the polytropic process in a single video itself. So to reiterate, it's a reversible process where both heat and work are involved and a specific combinations of pressure and volumes are kept constant. That's the polytropic process. The work done in polytropic process can be derived in terms of temperature and also derived in terms of pressures and volumes like we have made earlier. We have found a relation between Cp and Cv here, and we have solved a sample problem also to explain what's the meaning of that is. That's it. Thank you for watching. You can re-look into the video, and if you still have some kind of a doubt, you can just comment in the comment section. Thank you.